Hello there, and this is AQA A-level chemistry. Hopefully this is one of many videos that you're going to find useful. This video focuses on spec point 3.1.4, which is physical chemistry, and it's energetics. And this is the first video of 3, so there's 3 lessons in this topic. And this will focus on the introduction to energetics and calorimetry. As always, when we're covering a topic, we should always refer to the specification to make sure that we're studying the correct content. So we're going to start off by the introduction section, which is looking at endothermic and exothermic, and the term delta H or enthalpy, and the definitions for enthalpy of combustion, enthalpy of formation, and there's a third one we're going to look at that isn't on that spec, that is the enthalpy of neutralization. Let's start with some enthalpy profile diagrams. Now, you may have a knowledge of these from GCSE, you may not, but enthalpy. So let's talk about what enthalpy actually is. So enthalpy is a measure of the internal energy that chemicals possess. Okay, you could visualize it as the internal energy that those chemicals or those substances hold. Okay, so you can measure it, you can quantify it. So here in the profile diagram on the left, we've got the reactants at this level, and during the progress of the reaction, the enthalpy of the product is below the enthalpy of the reactants. That means that enthalpy has been lost. So this has a change in enthalpy and it's negative. This means that energy has been released to the surroundings. So the surrounding temperature has increased because the internal energy has decreased. And profile diagram on the right, this shows that the enthalpy has increased. So we've got a delta H that is positive. That's what the plus VE, that means positive. So the products have a higher enthalpy than the reactants. That means that energy has been taken in from the surroundings. So the surrounding temperature has decreased. So this would be your endothermic reaction, which is a decrease in temperature, but an increase in enthalpy. And this is an exothermic reaction where there's a decrease in enthalpy and an increase in temperature. Okay, now you may have seen these profile diagrams where they also show the activation energy. And this section here, which is from the reactants to the peak, this is the activation energy. And likewise, we have an activation energy on this side. Common mistake here is that people believe it's from the products up over, but it's not. It has to be from the reactants to that peak. So you can see in the profile diagram on the right, the endothermic, the activation energy is actually greater than the delta H here, look. So it's from the reactants to the peak of that curve. Right, definitions then. So there's 3 definitions we're going to look at. Enthalpy of combustion, delta H. So this delta H means change in enthalpy, little subscript C for combustion, and this theta up the top is telling us that it's in standard conditions. So the definition is enthalpy change when 1 mole of a substance completely reacts with oxygen under standard conditions. That's a definition. You could be asked to recall that in the exam. Let's have a look at how we can represent these with equations then. So we're going to look at 4 examples and we'll do the enthalpy of combustion for these 4 substances. So what we're doing is we're reacting these substances with oxygen. So I must always have oxygen as a reactant plus the substance that I'm measuring the enthalpy of combustion of. So we'll always have, and it has to be 1 mole. I have to leave this as a 1. I can't change that value in front. So it must be 1 CH4, 1 C, 1 Na, and 1 C2H5OH. I'm reacting them all with oxygen. First one, hydrocarbon, reacting that with oxygen will make carbon dioxide and water, but I need to make sure it's balanced. Remember, balancing it, I can't put anything in front of the CH4. C's are balanced, H's are now balanced. Now I need to balance the O's. I've got 2, 4 on the right, therefore I need a 2O2, so the top one is balanced. Second one, carbon plus oxygen will make carbon dioxide. Remember, it must be complete combustion, because it's when 1 mole of substance completely reacts. So I can't have carbon monoxide or soot, it must be complete combustion. Is it balanced? That one's balanced. Next, metal or sodium plus oxygen, well, that was going to make metal oxide. Sodium is in group 1, will be +1. Oxygen becomes oxide, which is 2 minus. So from earlier work in ionic substances, the formula here for sodium oxide is Na2O. Now the temptation here to balance it is to put a 2 in front of the Na at the start, but I can't do that. I have to put a half here, because I can't put the 2 in front of the Na, because if I put a 2 in front of the Na, that suddenly becomes 2 moles of sodium being combusted, and I can't. It must be 1 mole of substance. So I must leave that 1 in front of the Na. And now I need to balance my oxygens. I've got half an oxygen on the right, so I need to put a quarter here. So we need to get confident and be familiar using fractions. It's not something that you've used before, so we must be able to balance using fractions, because the important thing is that this remains a 1. Okay, right. And finally, the last one's a little bit more complicated. We've got C2H5OH. Now, when we combust that, it's going to be complete combustion. So we're going to make CO2 and H2O. If this was to have contained sulfur, then we'd make SO2 as well. So just some things to look out for. You're basically combusting everything in here. So it's going to make carbon dioxide and water. I now need to balance it without changing the number in front of the C2H5OH. So this will become a 2. I've got 5, 6 hydrogens, so 3. Now I count my oxygens. I've got 4, 5, 6, 7 on the right. I've got 6, and there's an oxygen there, so that's balanced there. Next, we've got the enthalpy of formation, which is delta H, which is change in enthalpy, F for formation, and our little theta at the top, which is showing its standard conditions. So definition for enthalpy of formation is the enthalpy change when 1 mole of a substance is formed from its elements in their standard states under standard conditions. And similarly to the enthalpy of combustion, it is a definition that you could be asked to recall in an exam or a test. Okay, standard conditions are 100 kilopascals and 298 kelvins. You can remember them in any units, and the easiest units to remember is probably 1 atmosphere and 25 degrees C. So you do need to know what standard conditions are. Right, let's have a look at some examples then. So we've got 4. We're going to look at the enthalpy formation of CH4, CO2, NaCl, and C2H5OH. This time, what we need to do is show the formation of 1 mole. So there's CH4. We show the formation of 1 mole of CO2. And we show the formation of 1 mole of NaCl. And we show the formation of 1 mole C2H5OH. So this time, it's formation. So our substance that we're forming, it's a product. We show it on the right-hand side of the equation. And again, it has to be 1 mole. And now we have to decide the elements that make up these 4 substances. So CH4 is made up of carbon and hydrogen. Now they must be elements in their standard states. So hydrogen is H2 gas. Carbon, now you've actually got several allotropes of carbon, but it must exist in the most stable form, which is in fact graphite. So just carbon solid. Okay, state symbols are essential here. Okay, state symbols will be essential. You will be expected to put state symbols in these equations. Is it balanced? 1 carbon on each side? Yes. Hydrogens, I need to put 2 here. Remember, I can't change the value in front of this because it has to be 1 mole of this substance. And following the same, for the second one, it's going to be carbon, which is solid, O2 gas. That's balanced. So carbon solid plus O2 gas makes CO2 gas. Next one, sodium, which is solid, it's a metal. Chlorine is Cl2, it's diatomic from group 7. Balancing it, half. That's balanced. State symbols are essential. Fourth and final one then, elements here are carbon, hydrogen, oxygen. Oxygen is O2 gas. Hydrogen is H2 gas, carbon solid. Is it balanced? Well, I need 2 carbons. I need 5, 6 or 3 here and a half here. Again, fractions are very common here because we must ensure that we only form 1 mole of a substance. Right, I am going to give a definition for this one. So the enthalpy of reaction. The enthalpy of reaction is just an enthalpy change when the substances react in the molar quantities given by the equation. So in this case, the enthalpy of a reaction, you are basically given an equation of any reaction and the enthalpy change accompanies that reaction that you're given. Okay, so you're not expected to come up with your own equations here. You are given equations for these enthalpy of reactions. So it's kind of a bit of a cop-out really. It's a general term for any old reaction. It's just the enthalpy of a reaction, and it will always accompany an equation, and the values will always be appropriate or will match the molar quantity shown in that equation that you are given. Okay, so final one here, enthalpy of neutralization. This wasn't on the spec, but I did say I would cover this. Enthalpy of neutralization of delta H shows the enthalpy change. Neutralization, standard conditions. Now, for a definition, not likely to be asked this one, to be honest. It's far more likely going to be your enthalpy of combustion, enthalpy of formation. But definition for this one is enthalpy change when 1 mole of water is formed between an acid and a base under standard conditions. So whenever you get a neutralization reaction between an acid and a base, you always produce water. And the idea here is that there's an enthalpy change that will take place during that neutralization, and you must ensure that when you write your balanced equation that you have 1 mole of water. So let's look at an example. Sulfuric acid reacting with, let's think of a base here. Let's go with lithium hydroxide. That's going to form, definitely going to form water. It's going to form a base, which in this case is going to be lithium sulfate. Apply my rules there of ionic substances, lithium being 1+, sulfate being 2-. Balancing my equation, we'll put a 2 there. And we'll need to put a 2 here. Now that would be how we'd balance our equation. That equation there is balanced. However, that equation does not represent the enthalpy change of neutralization because that equation is representing 2 moles of water being formed. So what we need to do is divide the whole equation by 2 to remove these 2's, and we'll end up with a half and a half. Now you would never normally balance that equation in that way, but in order for it to fit the criteria of the enthalpy of solution, we must balance it that way to show that 1 mole of water is being formed. Okay, so the enthalpy of neutralization would be the enthalpy change in that reaction there, in those molar quantities, when 1 mole of water is being formed. Okay, so it's your turn now. What I suggest you do is you pause the video and you have a go at these 8 questions now. And when you're ready, unpause the video to see the answers. Okay, so the first 4 are enthalpy of combustion. That means that we are reacting them with oxygen completely. So in every single case for the first 4, plus O2, gas, plus O2, gas, plus O2, gas. Every single case. And we cannot change the number in front of the Mg, C2H6, CH4S or the CO because they must be 1 mole, because by definition enthalpy of combustion is when 1 mole of a substance completely reacts with oxygen. Now magnesium reacting with oxygen will be oxidation. It's going to be magnesium oxide, which is MgO. Magnesium's in group 2, 2+, oxygen group 6, 2-. Its formula is MgO. That's ionic. It's going to be a solid. Is it balanced? No, I need half O2. That's the first one done. Second one is a hydrocarbon. We're going to make carbon dioxide, which is a gas, and water. Now, must be a liquid water because it has to be standard states, standard conditions. So if you were to actually burn ethane, you would probably produce steam because of the exothermic reaction. However, because it must be the standard enthalpy of combustion, it must be standard state, that must be a liquid. Is it balanced? No, I need a 2 here. I need to put the 3 here. So the carbons and the hydrogens are balanced. Time to balance the oxygens. I've got 4 from CO2 and 3, so that's 7. So I need 3.5 O2. That's balanced. Third one, CH4S with oxygen. So it's going to make carbon dioxide. It's going to make water. I've got sulfur here though, so the sulfur is also going to react with oxygen, which makes sulfur dioxide, SO2. Carbon dioxide is a gas. H2O is a liquid. SO2, this is the gas that's responsible for acid rain, SO2. And this is showing the impurity of sulfur in hydrocarbons. So balancing this then, carbons are balanced, sulfur's balanced, hydrogens, 2 there. Now I'm going to balance the oxygens on the right hand side. 1, 2, 3, 4, 5, 6, so 3 there. Done. And finally, the last one, CO plus O2. Well, carbon monoxide, that's actually a product of incomplete combustion. So it will now go completely, which is carbon dioxide, which is CO2, gas, and I'll need a half in front of the O2. There we go. Right, for the last 4 then. For the last 4, I'm looking at the enthalpy of formation. So this time, my product is going to be the substance that I'm forming. So Na2O on the right, and then C2H5F gas on the right, SiH4 gas, and finally CaOH2 solid. Now I have to form it from its elements. So the elements in Na2O is sodium, which is a metal, solid, and I need 2 of those. Reacting with oxygen. Oxygen is O2 gas, and it has an element in its standard state. So put a half here. Remember, I can't change the value in front of the Na2O because then it would no longer be the enthalpy of formation. It would be twice the enthalpy of formation, for example, if I put a 2 there. Next one, I'm forming it from carbon, which is a solid, it's graphite. The most stable allotrope is graphite, so I need 2 of those. I also need hydrogen, I need 5 of them, so that's 2.5 H2, that's a gas. And I need F. F is group 7 element, it's diatomic, it's F2, so I need half F2, and that's a gas. SiH4, Si is a giant covalent substance, Si solid plus 2H2 gas. And the last one, it's made from calcium, which is a metal solid, and oxygen, which is O2, which is a gas, and from H2, which is a gas. Is it balanced? Yes, it is. Okay. Right, moving on then. Moving on to the next section of the spec, which is calorimetry. Now, calorimetry is a topic that you've most likely done at GCSE physics and GCSE chemistry, and it's using this equation of MC delta T. Okay, and you will have used it in both chemistry and physics. So we're going to look at being able to use that equation. We do need to know it, and we need to be able to use it and carry out calculations, being able to rearrange it on several different scenarios. There's also a required practical that fits in with this. So I am going to very briefly touch on the practical methods, but I'm not going to explain it in detail. We'll save that for a later video and when we cover required practicals. So very briefly then, to look at the 2 different types of calorimetry. There are 2 different types. We can either use the reaction that's taking place in solution. So if your reactants are solutions or liquids, then you can use this type of calorimetry where you just liquid or reactions taking place in solution. The second type is using a flame calorimeter. So we're going to look at the 2 different types. So If your reactions are taking place in solution, you can literally use a polystyrene cup, and we'll use a polystyrene cup because it's insulating, and we put that inside a glass beaker just to add more insulation, to make sure it's nicely insulated. And again, a lid that adds more insulation because we don't want heat loss here. Any heat that's been lost means we're not measuring it, because we have a thermometer and we measure the change in temperature. Your reaction mixture's in there, so during the reaction the temperature is going to change, and this is what we do. We would record temperature every 4 minutes. You would record the temperature every minute, even for the first 4 minutes before you even add them together. This makes sense when you do the required practical, so look out for that video as well, and look out for that practical. We must make sure we know the volumes and concentrations of the reactants. So flame calorimetry then. So flame calorimetry is usually used to calculate the enthalpy of combustion of a substance, and you would use a spirit burner. So here we'd have our fuel in here, or substance being burnt. You would ignite that fuel, and you would use the heat being released to heat up some water. Okay, so we'd have a glass beaker with a lid to insulate it to prevent heat loss, or reduce heat loss anyway. We'd have a thermometer for measuring the temperature at the beginning and temperature at the end. We'd have water in that beaker. So what we're doing is we're carrying out a reaction underneath by burning the fuel. That energy from the fuel, the energy being released, is being used to heat up the water, and we're measuring the changing temperature of that water. So things we need to know here is we need to know how much water is being heated up, so the volume or the mass. We would need to know the initial temperature of the water and the final temperature, so we could work out the change in temperature. We'd also need to know how much fuel has been used, so that we can convert that into a kilojoules per mole, because we need to know how much fuel has been used, how much water has been heated up, and we'll carry out a calculation based on that. So carrying out calculations then, hopefully you're familiar with this. We've got Q equals mc delta T, where Q is our heat energy. So this is our heat energy, and this will be measured in joules. We've got M, which is the mass of the substance being heated, which in our case is water. Even if it's solution, we take it as water, so the volume of your solution is your mass. And C is the specific heat capacity of the stuff being heated up, which again is always water, and you'd be given this in the exam, 4.18 joules per Kelvin per gram. And finally, delta T, that's the change in temperature, and again that's of the water, so it's a change in temperature of the water. That's a common mistake that people make, is quite often they get the incorrect mass and temperature change. So make sure it's a temperature change. Temperature change can be in kelvins or degrees C, but this here, the mass of the substance being heated, which will be the water, okay, or the solution. But if it's solution, it's in water, so it will be of water. Okay, so let's do a couple of examples then. So the first one, we've got 0.055 moles of solid lithium chloride were being dissolved in 30 centimeters cubed of water in a polystyrene cup. So this sounds like it's our reaction taking place in a solution. Temperature of the water decreased by 9.4, so we've got our delta T is equal to 9.4. I also know that this is endothermic, so I'm going to make a little note of that and I'll come back to that. It's endothermic because the temperature's gone down. We've been asked to calculate a value for the enthalpy change, so I'm going to use Q is equal to mc delta T. My M in this case is 30 because that's my volume of solution, and water has the density of 1 gram per centimeters cubed, so I'm going to have 30.0. Specific heat capacity of water is 4.18. You haven't been given this in this question because this is one of my examples. If this was an exam question, you would be given that within the question, and the change in temperature is 9.4. So I'm going to work out my heat energy here. So 30 times by 4.18 times by 9.4 equals 1178.76. And that's going to be in joules. So this comes out in joules. Now I need to work it out in kilojoules per mole. So this value that I've just calculated was for 0.055. So what I do is I divide my value by the number of moles. So 1178 divided by 0.055, that's going to give me per mole. And that comes out 21432. That's joules per mole. I need to convert it to kilojoules per mole and 3 significant figures. So that comes out at 21.4 kilojoules per mole. So that's my answer for the first one. And I'm putting a plus sign here because it was endothermic. Endothermic means that the delta H is positive. Okay. Next one. 200 centimeters cubed of water was heated by burning ethanol in a spirit burner. Use the data as below. Calculate a value for the enthalpy of combustion of ethanol. Well, combustion of ethanol is when 1 mole of ethanol is burnt, and it's going to be exothermic because it's a combustion reaction. So I know it's going to be exothermic. Hopefully I'll see the temperature increasing. Yes, I do. So I'm going to find my delta T, which is the rise in temperature. 41.5 take away 21 is 20.5. My mass, don't get drawn in to thinking this is your mass here. Okay, this isn't. This is only going to help us with the fuel. The mass is the water that's been heated up. So my mass here is 200 grams. That is the most common mistake that people are going to make here, is they're going to do Q equals MC delta T. They're going to take the mass of the fuel when actually I'm working out the energy being absorbed by the water. It's the mass of the water, the specific heat capacity of the water, and the change in temperature of the water. It's all about the water. So let's calculate a value for this. So 200 times 4.18 times 20.5 equals 17,138. That's going to be in joules. I want this in kilojoules per mole. So I need to divide it by my moles, and that's where this mass comes in. I can find my mass of ethanol. C2H5OH is ethanol. My mass is 102.56 take away 101.88, 0.68 grams. So I'm going to convert this into a moles. Moles is mass over MR. 0.68. My MR is 12 times 2 plus 6 plus 16, which is 46. You can work that out for yourself. The MR is 46. So my moles are 0.68 divided by 46, which is equal to 0.01478. So I'll now divide this value by 0.01478. And that will give me 17138 divided by 0.01478 equals, and I'm going to convert it to kilojoules. I've got a value of 1, and I'm going to go 3 significant figures, 1160 kilojoules per mole. Okay. Okay, over to you then, your turn. So I want you to look at your pink books, which are your self-assessment books, and you're going to have a look through the energetics. If you haven't done the questions on enthalpy of combustion, enthalpy of formation, enthalpy of neutralization equations, go ahead and do that. And then there's also a couple of sections on calorimetry questions. And again, with these pink self-assessment books, you do have the answers at the back. So hopefully that was useful. This was only lesson 1 of 3 for this topic, so look out for the other 2 lessons.